All right. I'm here today with Nicholas Nicolaou and Kishori Kanwar. So, Professor Nicolaou, long-term collaborator, now member of Optimum. Dr. Kanwar, very long-term collaborator and now CTO at Optimum. My name is Muriel Medard, and I am co-founder, along with Kishori, of Optimum. And I've been, for many, many years, professor at MIT, holding the NEC chair in software science and engineering for professor in the electrical engineering and computer science department, and leading the network coding and reliable communications group. So just as background, Optimum, which is the company that all three work on, is the company that is doing the IP for Web3, the Internet Protocol for Web3, looking at decentralized data optimized, hence the name Optimum movement. And today we're going to chat about the trilemma, something that many folks in Web3 and blockchain know, discuss, comment on. And we have done some recent work on that, which we've posted. We've had some posts, but we thought it'd be fun, just the three of us as collaborators, friends, colleagues, to chat about it and share our discussions with a broader audience. So we're hoping that you'll enjoy our chat, and maybe this will lead to your own discussions with your own colleagues online, in person, and just to start some more intelligent discussions. So with that, I'll start with you know, let's say the origins of the trilemma, and particular the work that Nancy Lynch, just as a little bit of background, my colleague Nancy Lynch actually held the NEC chair in software science and engineering before me. And she and I co-supervised Kishori when he was a postdoc at MIT. And of course, she has worked extensively with Nicholas. So, she's a bit of she's an advisor to companies. She's a bit of intellectual conjunctive tissue here. So, I'll just open that question of, the origins and what the underlying theorems are. Maybe I'll start with you, Nicholas, and then Kishore, if you want to chime in.
Yeah. Thank you, Muriel. Yes, I think the origin of the trilemmas stems from initially from the cap theorem, where that was proposed, if I remember correctly, in a conference, and Nancy with a colleague, Seth Gilbert, they took the opportunity to prove that trilemma, the CPA, that was correct. And that had to do with consistency, partitioning, and availability of data. They prove in that in a paper that indeed there is a problem in guaranteeing all three of those properties in a single distributed system, meaning that we can either guarantee consistency with partitioning but not availability, partitioning with availability without consistency, or consistency and availability without having partitioning. And in simple terms, all three cannot coexist. This is what the trilemma says. Within that paper, they managed to show that indeed there was a problem with the CPA, and all three cannot coexist. However, two of them can coexist in a distributed system. Following that, we have the trilemma that is applied in blockchain, which talks about three other properties related to the first, however, termed in a different way, which the three properties that we have in the blockchain trilemma is the decentralization, scalability, and security. And upon this, there were many discussions that we can go through and take a closer look, I guess, in our discussion.
Yeah,
Yeah, no, thank
thank
you.
you, Nicholas. Kishore, did you want to add
Yeah,
something to that?
yes.
Yeah.
No, this is a great point actually, Nicholas, that mentioned that although the trilemma in blockchain talks about three different, properties, but the very style of reasoning or thinking originates in cap theorem. Because you'd see system designers who are not doing directly any theoretical work, they use the cap theorem as a means to adjust the trade-off, which two to pick. And you can have any two, but not all, in a realistic network. So now that result was also, there are some a lot of gray areas that when you actually bring the model to realistic systems, what does it mean to be asynchronous? If a
Right.
connection is disrupted for a long time, is it asynchronous or it's failed? And there's a very nice article by Professor Lynch and Gilbert Seth in one of the ACM communications issue dedicated entirely to the cap theorem. And now
Mm.
when it comes to the blockchain world, it's very interesting that they actually modeled in a very similar way or framed, but except it is not proven theoretically. And that's where, a lot of the discussions or confusions, you can say, you know, continues. And it's very important to understand, get deeper into.
Agree. And maybe just for folks, because um, the consistency part, which is in the original cap theorem, I think is a little bit misunderstood. And maybe that's a little bit why, as you mentioned, the trilemma is an informal representation of the cap theorem, but in that informality, maybe some uh that some of the original rigor of the cap theorem has been lost. And in a way, the trilemma is a little bit too um, pessimistic, right? And partially
Mm.
because you don't have those definitions, right? And in particular, what you don't see is consistency. That right? In the original cap theorem, there's consistency, which has a very specific meaning. And in the trilemma, you don't have consistency. And I think that's maybe one of the core places where there's some level of uh, disconnect between the informal, let's call it folk theorem of the trilemma, which has issues and has, in my view, but I'd like to hear everybody's view, sort of made people think too pessimistically about what can be done versus, the original cap theorem, which is a theorem, where the proof is correct, but a proof is correct for those very particular, very uh, specific definitions. Yeah.
Yeah,
Uh,
Mhm.
yeah. So I'd like to hear how do you guys like to explain, when you're trying to tell somebody about
yeah,
consistency,
yeah,
who's just not a
Yeah.
who's not somebody who's been working in this particular area of distributed and decentralized system computer science. How do you like to explain consistency? I can go first. I could
yeah,
say how
yeah,
I give it
wonderful.
as an example, and then I'd love
Hmm.
to hear is, what I tell people about consistency is like, you're storing. When you store, it's like you have a closet, right? So I go and I hang in a dress, right? We're sharing, you have reading and writing. So the writing is I stick stuff in the closet, right? So I go and I stick in a dress, right? And then Kishori comes in later and he sticks in a jacket, right? Now, Nicholas comes in, opens the closet to read, to see what's in there. Ideally, he sees the most recent state, which is the dress and the jacket. He might see an old state. He might see just the dress, but he's not going to see just the jacket. That never happened, right? That's how
Hmm.
I like to describe it. So that's
Yeah,
the way I describe it. When I'm
yeah,
just talking to folks
mhm,
informally, it's like, what is this? But I'd love to
yeah,
hear how you guys
yeah.
describe
Yeah.
consistency.
Yeah. Go ahead, Nicholas.
This is a very nice example, and I really like it to bring it to, in the real life
Yeah.
problems and issues. Uh, and indeed, consistency. This is what consistency is. Sometimes when I try to explain consistency, I say I'm taking it in terms of copies of data. You have number of copies of data, and what you want to do actually is to keep those copies the same, right? So if you make a change on a copy, you have to make sure that all the copies get this change. Okay, and this is a consistency. And as you said, Muriel, basically the problem stems, the CAP theory stems from the assumptions that we make in the system that there is asynchrony, so we don't move in synchronous steps inside the system. And also, the other thing is failures that we do not control, and we don't know whether they happen if we do have synchrony. Uh, and that's why consistency, it gets tougher to guarantee when we have these assumptions in the system. Whereas if we had synchrony and we know that everything is ideal and nice and everybody moves in steps, then if I change a copy, then I could change all the copies at the same step. So
Yeah.
everybody will
Yeah.
move in the
Yeah.
same step. What do you think, Michelle?
Yeah, I think it's a very interesting concept. We know it intuitively, we feel it depending on different situations. At the same time, it's so hard to formally describe and argue about it, but then it's very far away from it feels it's very far away from the practice. For example, if I'm writing a program, I update a variable, then I read it, I expect whatever just I updated. But now if I go to multi-threaded program, that variable might be touched by different threads that are scheduled by the operating system. Then you go to distributed systems. It's not just threads in one machine now. It's a bunch of machines connecting over to the same location, and they may fail. And in blockchain, they may be Byzantine. So now what is the underlying then behavior that we are expecting? It's the researchers, they define it as an object, abstract object, and it has some behavior. And it is essentially the behavior, and it does not directly talk about how you implement it. It's a behavior you exhibit. And that's very, very, very interesting. CAP theorem was about a data store, data access. And blockchain, you care about a different kind of consistency. Maybe it respects the overall definition of the blockchain, how the EVM, or in the case of Ethereum, should work. Is the behavior consistent?
Yeah.
That needs to be carefully discussed and thought about.
Absolutely, absolutely. And I think, from closets to multi-threaded programs to, copies everywhere that you have to update quickly. I mean, this illustrates, the inherent difficulty. And I would say not just distributed, but really decentralized, right? Because to some extent,
Absolutely.
if it's distributed, then, you can still have a leader that tells
Yeah.
people what to do. Even if it's asynchronous, you basically, the leader can say, I'm not going to do anything until I hear from everybody, et cetera, right? But when it's truly decentralized, like in blockchain, like, everybody's just doing their thing. Good luck with this,
Yes.
So I wanted to go back to, I wanted us to spend a little bit of time on consistency because I feel that that's maybe one of the concepts that's most tricky, and somehow diverges, but I'd like to hear what you think. It diverges most in its definition from the informal trilemma definition, right? Because what we're talking about here is effectively what is the mismatch between the CAP theorem, which is theorem, 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 and the trilemma, which is more of a directional type of folk theorem, let's call it that way, right? So what do you think are the main points of divergence between the CAP theorem and the trilemma?
Nicholas, do you want to?
Yeah, I can try to go first. I think, okay, one of the main parts that is missing from the blockchain trilemma as we know it right now is, as you said, here is the consistency. Consistency is something that is not referred explicitly into the blockchain trilemma, although I believe that notion is hidden without the properties that they are looking at. First of all, if you think about blockchain it needs consistency in its core. Why? Because we need a single copy of a blockchain to be replicated among distributed decentralized peers, right? And everybody needs to see a consistent view. Otherwise, we're going to have a problem, right? So, in order to generate this consistent view, what they are, what we are using in blockchain define exactly these three suffers from these three properties that we have. Not suffer, but is dependent, I would say. Uh, because in order to establish consistency, we exactly use consensus, where everybody agree on a single copy or on a single
Or
view
enough
of the
people agree.
blockchain.
Yeah.
Exactly, enough people
Yes.
agree,
Yeah.
and when enough people agree on that copy, then we assume that okay, this blockchain is what we are going to be using from a point in execution and above. So uh, the the three properties that they have in the blockchain trilemma essentially focus on the solvability of consensus because we have decentralization, how much we can decentralize so as we have more people participating in this uh, uh, in the consensus in the agreement protocol. We do have security. How can we protect consensus from malicious acts? And we also have scalability, which means how can we solve consensus as fast as possible once we have decentralization in the system. And and essentially everything comes down and collapses to having consistency in
Yeah.
blockchain.
Right.
So
Yeah.
so
And
that's why I think they are very related to it.
yeah.
What do you think,
In,
Kishore?
in fact, I feel that when we talk about the trilemma, we talk about security. I mean, security might mean a lot of things. One,
Correct.
somebody could be, lost their money because somehow somebody got access to their keys or etc. But it does not mean it's a security violation of the underlying chain. To me, the security needs to be defined in a more formal way, maybe as a
Yes,
sequential specification. How should this system behave when your clients interact with it? As long as that behavior is respected and not violated, then to me, it's a security. Essentially, it might be called safety in other literatures. Safety is preserved property.
I think
So that's
that's a really good point. Sorry, go ahead.
yeah,
yeah,
Yeah.
yeah. So that is. Now, one other aspect Trilemma brings, I find it fascinating, is that in most of the formal way of analyzing a distributed systems, we often think that local computations are actually negligible compared to network communication. Here, we are executing a smart contract at every, in different nodes. So it is doing computation, actually. And that also brings another aspect to scalability. So it is indeed, you cannot just execute the code of a smart contract in negligible time. So those are several dimensions we need to think about.
mhm,
You bring up an excellent point, Kishore, and I'm going to just pick on that because actually, remember when we started working together with Nancy on bringing, coding to consensus systems. One of the big things we started looking at together was the cost of communication, the cost of networking, which was generally not taken into account in the literature up until that point. Remember that? That was definitely one of
Yes,
the
I
big
remember that.
motivating, yeah. When we started working together, whatever, 12 years ago. Let's
Yes.
not let's not even try
Yeah.
to
For
think how
example,
long.
storage cost. Everything is about storage cost, different costs, which was very
Exactly,
interesting. Yeah.
exactly. And I think that that's also something that the trilemma suffers from, which is that absence of um, taking into account the cost of the propagation. right?
mm,
Versus just, and as you said, the idea that the compute is taken into account, maybe the storage is taken into account, but that, if you have computer, you have storage, and you don't have a way of moving the data back and forth between the storage and the compute so that the compute can happen, because the compute has to happen on data, otherwise what are you computing on? That missing part is still reflected in the current trilemma. That's my view, that's my opinion, but opening it up for you both to comment on that.
Yeah, Nicholas, what do you think about
uh, yes, I mean, indeed, talking about storage and computation right now is the big part of what we are doing in blockchain, right? Whatever we store information, and then we try to um, compute, as you said, over smart contracts in order to be able to reach a state that everybody's going to be there. And uh, computation is a big part of it. So we cannot distinguish computation from communication, because one great part of the whole ecosystem is going to the computation. Uh, However, I believe that communication, even though um, is computation is a big part of blockchain, communication remains as one of the central overheads that we have in the system. So uh, we need to find ways to see how communication can be reduced or can be optimized in a sense, so as we can have uh, either solve or see if there is a solution to the problems that we face in the trilemma, or to show that, okay, even if we do have this optimization of communication, we still face some bottlenecks that may lead to the trilemma.
Yeah, so actually it's very interesting that when you talk about decentralization, and each node is involved in state transition of the replicated state machine, they may diverse, then you have actually violated security or safety.
Yes,
The
exactly.
only way to keep them in check is to have guardrails of communications, because how would
Correct.
they know that they are not moving apart from each other in terms of the state?
Yes. Yes.
Mhm.
Actually, even if you only had two nodes, one which was basically your CPU and one which is your memory, and it's very clear who does what, and there's only a single copy of the data in the memory, and somehow, you had a very narrow bus or columns between them, your
Right.
system's going to be terrible. Right? It's just
Yeah,
like,
Yes.
and it's not because, there's some clever issue here about decentralization or anything. It's just like you can't get there, right?
Right.
mm,
So I think that's core. Um, we together have actually talked about, the end of the trilemma. Certainly we've had some sort of fun content on Optimum about the trileminati and so on. Um, and maybe we can go a little bit more now that we understand that there is a theoretical underpinning to the trilemma, but it's not the trilemma. And in
mm,
particular, one should not over interpret the trilemma, right? Because in a way it's too loose, it's not rigorous,
mhm,
and therefore it's very easy to misinterpret rather than just, let's say, a helpful vague reinterpretation of the cap theorem. One can think that it's actually something that's telling you impossibility results that are not there. I want to get you feeling, get the work that we do, together, at Optimum, how it, makes it so that some of the interpretations of the trilemma were not correct. You know, And maybe, one of the things I can do is start with an example, right?
Mm,
And then to hear everybody's opinions or your own examples or maybe comments on mine. Um, let's think of scaling, right? Um, if you don't code and you have a network where, even before you're trying to do computation or anything, you're just trying to get data across. And you have some fraction, either because of failures, Byzantine attacks, or whatever, some fraction of shards that don't get through. And I just have the simplest network, just a daisy chain, link one, link two, link three, etc. Right? And if I code only end to end, so the kind of uh, legacy codes that are currently used by other companies in blockchain, say a read summon code or something like I don't know, like a traditional rateless code. Um, then what will happen is actually my throughput will not scale. It will go down exponentially with the number of nodes, right? So to me, that's a very clear idea that, okay, oh, well, I can't scale, right? Um, but while at the same time remaining, reliable, let's call it reliable and safe, reliable meaning that I have a reliable throughput, and keeping everything else that I need. So, but actually, if I do RLNC and I recode, then I can do that. Then I can actually get a perfect throughput. That's to say the maximum available throughput, and that throughput is now scalable. It doesn't depend on the number of hops, right? Whether I have 2 hops or a million hops, my throughput stays the same. Basically, I was talking about the fact that, what the example I just mentioned is one of those, whatever, ansatz, nostrum,
Yeah.
it's an example of what people believe, which is kind of like what the trilemma is, right?
Mhm.
It's a something that people believe, which has some root in reality, of course, but is maybe not a correct um, understanding of the theoretical limits as more, uh, an interpretation of something which is theoretically correct, but which is not a correct interpretation. And then also bringing in empirical experiences that people have had and which say, oh, well, I'm not able to do that, right? So, the
mm,
scalability that I just mentioned here, if you were to say, well, this would be an example of why I can't scale. But yet, if you do the math correctly and you recode, you actually can scale. So, that's my favorite, if you will, sort of uh, counterexample. And again, you can't completely give a counterexample to something
Yeah.
that wasn't completely defined, rigorously, but a counterexample to that, you know, general sentiment, let's put it that way. So
Right.
that's my favorite
mm,
counterexample. I'd love to
Yeah.
hear yours, Kishori,
Yeah.
and yours, Nicholas.
Yeah. So, no, this is very interesting. So I arrive at almost the same conclusion, but in a slightly different angle. So what I think is that the trilemma, as it is stated, even though it's not proven in any, under certain specific assumptions, or at least I do not see any well-defined, um, it's like a folklore. Now, different people will look at it from different points of view. Some people will think, it's too difficult to create a system. Others will think, hey, I have actually beaten the trilemma. And that's because there is no one clear-cut definition based on a formal way of expressing the statement. Now,
mm,
even with that, if you look at it, decentralization and security and scalability. If communication were extremely good, imagine, and almost like a, near, as best as it could get, then you can actually have a much better time with it. And you can circumvent this pessimistic aspect. Why? Because if communication is low and reliable, you can actually make the time slot synchronous steps, which is easier to deal with, much smaller. Essentially, you are making time go faster
Yes.
because, and that is the key, I think, because the other two are not, you cannot compromise security. It's a definition of what you mean by
mm,
safety. Number of participants you cannot eliminate, otherwise you'll wind up being a centralized system. The only axis that is remaining to be tackled actively is this communication and tied to scalability. That's how I look at it. I would love to hear
Mhm.
what you
Yeah,
think,
yeah,
Nicholas.
that's a really good point. Yeah, yeah,
Yeah,
thank you, Kishore. Nicholas, I want to hear your thoughts on it.
yeah. I mean, this is exactly the way that you described it, Muriel. Indeed, if you see it from that point of view, that scalability somehow can diminish, then basically the trilemma it cannot be compared with the cap theorem anymore. Why? Because there we saw that we can guarantee the two properties, but we cannot guarantee the third one. However, if we can guarantee scalability and we are able to um, be able to deliver messages in a fast pace, it means that decentralization and scalability they become one, and there is no problem of when we decentralize to guarantee scalability, and at the same time we guarantee security. So that's how the trilemma can go away, and and indeed, the lack of formal definition, as mentioned by Gishori, this is one thing that it's very important. Why? Because when we go back to the cap theory, there is a clear a relation between each property and a system behavior. For example, consistency is linked with safety. Availability is linked with asynchrony, and partitioning is linked with failure.
Right.
So we can directly see a connection between each property and a system behavior. So it must be the case that if we want to have like a formal trilemma, there must be a connection between those properties that we say with the properties of the system. And for now, there's a lack of definition, which doesn't help us to indeed say that okay, this is a trilemma, and this is why or why not. It is not bad. And as Kishori mentioned, there are so many solutions that we see in the community where they claim that they solve the trilemma by different mechanisms, either by reducing decentralization or by having some other optimizations that may lead to scalability. Uh, I believe that uh, right now what we have with RLNC is the closest one that's going to show that scalability and decentralization can coexist in a single system without any issues.
In fact, as you mentioned, if I can chime in, is that is why in Optimum, as you probably now realize, but I just want to bring it out for the listeners, audience, that whenever we want to solve a problem, we first define what is the specification, behavior of that system as we interact with it, without thinking who implemented it, what programming language, what technology. We don't even look at it first. This is the behavior we want. Once we pin down the behavior, we think about implementation. And then we try to show, and we show actually, that what are the behaviors we can derive from such an protocol algorithm that claims to implement those properties. And then we go to the systems. So this way, you can actually bring guarantee to what your system can provide or cannot provide accurately. And it's very good for application builders because they know exactly how your system behaves.
Yes, yes. And it's that sort of uncompromising engineering, rigorous approach that then actually makes things, safe and scalable. Because you don't go, well, I tried it out and it worked with 5 nodes. I'll be fine with 100 nodes. No, it will be. Actually.
Probably not.
That's right. It's not, prob's okay. I have had fun. Thank you so much.
Yeah.
This was
That was a great discussion.
This was a
Yes,
great
it was a very good
discussion.
discussion.
I hope that others enjoy it. We may put links to a couple of materials that we addressed, as part of this conversation. So Nicholas, Kishore, thank you both so much. Thank you.
Thank you.